So, at the end of our last video, we saw why or how we would use Ohm's law, V equals IR, on the entire circuit. We could take a total voltage, come up with a total resistance, and use that to find the total amount of current coming out of the battery. Now let's take a moment to talk about using V equals IR on components. So, all of a battery's voltage needs to be used up whenever you go around a loop. Now in a series circuit, there's only one loop, so this is pretty straightforward. There's only one path you can possibly take, and you need to spend all your voltage along that path. In a parallel circuit, however, there can be multiple loops, and so you need to make sure that on any given loop you take, you're spending all of your voltage. Now this actually is why on in parallel circuits, the voltage drop across each is the same. So if we're going to spend all our voltage, say we got a 12-volt battery here, we could leave it, spend 2 there, then we could spend 4 there. That's 6 total. We need to spend 6 more. It means we use up our 6 remaining on that last resistor to make sure we've spent 12. All 12 volts by the time we get back to the battery. So we leave with 12, we spend 2, we're down to 10, spend 4, we're down to 6, spend the rest 6, down to 0. We get back to 0 by the end of our loop. In parallel, there's only one resistor we hit. All of the resistors are in parallel, so on any given loop, we only cross one resistor. So if I have 12 volts, while I go around the loop, I only hit one resistor. I better have spent all 12 volts there. Alternatively, I might have taken this middle path. Well, I leave with 12 volts. I only hit one resistor. I have to spend all 12 volts there. Same goes for the last path as well. Any path I take, I need to spend all 12 volts, so the voltage drop across each resistor in parallel better be the same. That way I can keep my voltage budget the same. And it turns out this actually starts with the battery itself. There are some pieces of wire in there with the battery to get the battery connected to the circuit, and you're going to have some losses there. This is typically small, and it's a small internal resistance. And that internal resistance uses up some of the voltage. It acts just like a resistor itself, and you have a voltage drop across it. So it turns out that something like a 12-volt battery is actually a 13-volt battery, but they've already accounted for that little bit of energy or little bit of voltage that is lost inside the battery itself. And if you were to draw this in a circuit diagram, usually they box in the battery and this little internal resistor that they often label as RINT, R internal for internal resistance, and that's all in a box indicating that that resistance stays with the battery. You can't get rid of it. So that being said, I will tell you guys, we're probably going to ignore internal resistance in most problems. You might be asked about it, and I want you to be aware that it exists, but we're not going to be nitpicky and include this. That's for electrical engineers, people doing more detailed study of circuits and electronics. They need to account for these types of things. But I wanted to make sure you were at least aware of it. All right, so components consume voltage. There is an amount of current flowing through them. There is a resistance that they have, and you can compute the amount of voltage they use by multiplying the current through an object times the resistance of that object. Things that consume voltage are referred to as the load in a circuit. Now I say that, and you're probably starting to think, wait a second, my light bulbs say watts. Where does power come into all of this? We've talked about voltage, current, resistance, amps, volts, ohms. All of these things are kind of familiar, but watts certainly play a role. So where does power fit into all of this? Well, here is the equation for power, or really 3 variations of it. This is the fundamental one. This is the one that I have memorized, that I always go to in my mind whenever I want to compute the power of a circuit or the power of a component on a circuit. P equals IV. Well, we also know that V equals IR. What if we crammed a little IR in for V? Well, we end up with I squared R. Or alternatively, we could substitute for I and we would get P as V squared over R. You can use these shortcuts if you want to. Say you're given a current and a resistance and you're asked for power. Well, boom, you can plug them in. But we know that V equals IR. If you have two of the three between V, I, and R, you can always solve for the other one. So there's no absolute reason you must ever use one of these, which is why I always use P equals IV. And when we go to solve circuit problems, I think you'll understand, because I'm often going to get all of the information. I'm going to get all the I's, all the V's, all the R's before I start answering any questions. And so we can really use whichever of these equations we would like. So P equals IV is my go-to, but you can certainly use the others as well. Well, like the voltage equation, or like Ohm's law, V equals IR, we're going to use power for both the entire circuit as well as for individual components. We'll do P total equals I total V total for the entire circuit, or P1 equals I1 V1, P2 equals P1 equals I1 V1, P2 equals I2 V2, P3 equals I3 V3, and so on and so forth for each individual components, however we've decided to label them. And we have a similar rule. Just like for a battery, all the voltage needs to be used up on a given loop. The power needs to be used up by all the components. So it's not just about a loop, it's about every piece inside that circuit. The battery's power can be computed as I total V total. If we then add up all of our individual components' power consumptions, they should add up to the total power. So if we look back to our little circuit diagram, for series this would be pretty obvious. Yes, you have to go through everything in a series circuit, so you're always going to include them. But for parallel, say we wanted to look at the power consumption, we don't just think about one loop. We need to add up how much power is consumed by all the individual pieces. And each piece should use as much power. If we add up all the pieces, they should use up as much power as the battery provides. So between the voltage loop check and the power check, you should be able to look at your answers when solving circuits and have an idea if they could be right or not. This is sort of the last step of our problem-solving strategy. Is my answer reasonable? Well, if the powers make sense, if the voltages around loops make sense, that's a good check. It's a good consistency check, or what we call sanity checks, just to make sure you're not going crazy, that it actually worked. All right, but that actually is the last of our notes on circuits. I think at this point it will be best if we just look at some examples. So we're going to have a series of videos now looking at series circuits, parallel circuits, and I'm actually going to do something that's a combination of the two. Will be our last video for this chapter. So stay tuned for that. There's some exciting stuff coming up. I love solving circuits. I think you guys will as well. I refer to them as the Sudoku puzzles of physics, and I think you'll see why shortly. So look forward to that.